Ronnie, Contractor, solution architect at Cisco for utilities and especially in this area. So a lot of local knowledge. Bring us home.
All right. Well, first of all, good afternoon, everyone. Hope you're all enjoying the forum to what we've had today, and hope you find that it's all been of value. I certainly have, learning some of the stories from David at BC Hydro and also the innovation that Itron has been undertaking with their new technologies as well. What I was going to talk to you about was a customer case study that we, as in the Cisco services team, worked on recently, which was with Western Power Distribution in the United Kingdom. So, just a brief overview of what I'm going to talk about, just some of the emerging technologies and the evolving communications that were employed, just the methodology, the framework that the Cisco team takes to exploring these kinds of projects. I'll then go into the actual case study. There were 4 intervention techniques that were explored as part of this trial. I'll give you an overview of the solution itself that we put together for Western Power, and also then the project learnings that came out of this particular customer and how that information has now been disseminated so that you are all free to see the same information as and when you need. So, just quickly, as you know, and you've heard all day long, we're moving from a world of limited sensing to much more deeper situational awareness. We're moving from a centralized cloud-oriented model to now looking at these distributed, what we call fog or edge computing type of models and architectures. And we're looking for movement away from those proprietary-based solutions to an open standard, open architectural platform. That's what we're looking for in these new networks, particularly as we look for the larger scale. Importantly, we're also moving away from that batch-based processing model, which was what took place traditionally, if at all, to now we've got real time there, but it's almost sometimes near real time, which sometimes is more reflective of the reality. The more we can push out to the edge though and get faster responses, the better that we're going to get towards that real-time decision-making capability. So what is a smart grid? You've heard different definitions from different people. Paul enunciated a different definition from AMI to smart grid 1.0, smart grid 2.0. The way I'd like to present it to you is to think of something that is in a stage of evolution. If you think about many grids, particularly at the secondary substation level, today they're not even able to be viewed by a distribution company. Most distributors don't know what's happening in the secondary transformer. So step 1 quite often is just to get the ability to observe what is happening in their own environment, the ability to monitor without even actioning any of the information that is there in the field. Step 2 might be to take that tentative step to go, well, we can now monitor it. Can we control it? Can we give control to our operators, particularly our human operators? We're still in our control rooms, they're still part of our outage management teams, etc. Can we give them some form of control? When we get to that point of maturity as an organisation and we can push on to the next level of advancement, we can then start to take on that automated functions. Can we start to automate functions and remove the control room operators from the decision making and the action requirement, and they're becoming more again into that observational role as opposed to the actioning role of control. That's where we start to get that automated capability, and that's where we see some advanced SCADA systems moving in that direction today. And then when you get to this longer range view where I think BC Hydro is starting to approach now from what Dave was talking about earlier, is this more integrated approach where we start to get different subsystems talking to each other, much the way Paul was talking about some use cases that have not even been truly thought through, but having metering technology talking to distribution network technology, it's something that's coming. It may not be here today, but the platforms that are being deployed with these 20 and 30 year life cycles can now start to take these future use cases into account. And that's where we're moving towards as we get to a smarter grid. So as you can see, we're moving around from different areas. We've got requirements for precision timing in different parts of the smart grid, particularly for the substation environments and protection networks, utilising layer 2 boost-based traffic, as you would know, coming from the protection function well. We're looking at pervasive security right through the smart grid, ensuring that those meters that may well now be talking to distribution assets cannot be not only tampered with at a physical level, but more importantly at a cyber level, that we cannot have a customer putting in a false command into that meter that could then action some sort of distribution network device, effectively causing a greater problem based on cyber threats. We're looking at the requirement to support enhanced quality of service in the network. As we start running these multi-services networks, we need to be able to prioritize what traffic is most important and needs to be honoured through this network and what traffic needs to be deemed to not be as important. All of this intelligence needs to be combined together to create that multi-service network capability. How do we do this? How do we start? We take a look at our existing service catalogue that we're providing our operational customers within utilities today. We're looking at their existing TDM infrastructure, particularly they would have dark fibre or PDH, SDH multiplex type network in place. Some would even have DWDM infrastructure in place. How do we start to evolve those technologies and move them up toward IPM type service offerings, field area network offerings, neighbourhood area network offerings, such that they can cover an entire service territory and provide that 100% coverage that we're striving to achieve? How can we integrate those new services that are coming on based on regulatory requirements, from advanced metering initiatives to distributed generation to microgrids to distributed storage? How are we going to get all that information back into our business so that we can make intelligent decisions of that? How can we map our new use cases that we're identifying and our future use cases to a place in the network such that we can choose the right technologies for the right outcomes and make sure that the comms choices that we're making are built for fit the requirements that we're going to be asking of our infrastructure. And so what are those factors? When we look at all those existing factors, from functional requirements, our existing networks which we need to keep supporting for live or energized circuits, our existing IP infrastructure, how can we build into that a modular environment that the entire utility organization can organically continue to grow but also continue to manage, particularly as the number of devices starts to go from the current thousands to potentially 10,000 enterprise endpoints up to the hundreds of thousands and really into the millions or tens of millions of endpoints as we begin to bring on not only the metering capabilities but the distribution network capabilities. So what Cisco does is we take a view of looking at the business framework and the influencing factors for any given utility. We start by looking at what are the internal and external influences on a given customer in a given market. The regulatory outcomes are different in every environment, and so we take that into account. We look at the market forces that are there. For utilities, it's typically not a competitive driver that you're competing against another company. You're actually just trying to improve the service that you're providing for your customers, because inevitably it's a monopoly infrastructure, it's a monopoly providing service offering. We're looking at the use cases and the utility of future side applications that are going to be needed to be supported. And typically we look at it from a 2 to 5 year viewpoint for a utility when we start talking to them, but have a view of what's coming up into potentially the 10 to 15 year time frame, because as you can see from the example of BC Hydro, David talked about starting in 2005, was it, when you began your work? And here we are in 2015 and just still just transitioning across to IPv6. So it's a long cycle to deploy these networks, and you do need to start having an idea of where you're going, because the decisions you're making today are going to come back in 5 or 10 years' time. You're going to have to live through the outcome of that. So a little bit of foresight today is going to help you as you move forward. We're looking at, as we place things in the grid, what technology components are required in the different places of the grid. We're looking at the wide area network infrastructure. We're looking at the data center environment. We're looking at the field area network. What technologies are going to be relevant in the field area? Today, 3G cellular is very common, but in 5 years' time, it's almost guaranteed that 3G cellular will be out. It will be gone. will be 4G will be mainstream, and 5G will be coming online. So will our routers and our access points that we deploy in the field today still be relevant in 4 years, 5 years' time? If we deploy cellular to the meter today as an option, we may deploy 1 million meters today, but will that 3G cellular solution still be available in 5 years' time, or will the service provider cut it off and force the utility to now go back and revisit every single meter again just to update a comms module solution? Is your technology going to be long-lived? So once we understand all those applications and use cases, we can start to help you derive the architectures that are going to give you that longer-term window, that 20-year lifetime, that 30-year view as to where you need these architectures to go. Because typically within the utility environment, by the time you finish your replacement cycle, you'll probably expended a good 5 to 10 years of time, and the technologies will have moved on and will continue to innovate and continue to go forward. We need to ensure that the technology at those points where there is a large scale, such as metering endpoints, won't be obsolete before you finish that rollout. So as you can see here as an example, if we take the dynamic asset rating use case, what we're doing is we're mapping those individual use cases to a place in the network, understanding how it overlays with the electrical network in particular, and utility customers typically understand their own utility infrastructure. From there, we can obviously highlight which substations or which physical locations are going to be impacted by a given use case, and we can map that into the technology domain, which is the area network solutions. How do you move from the use case through the physical electrical infrastructure, to the physical location and environment, to the technology domain, is the translation that needs to take place for each of those use cases. Typical comms requirements that you'll always find a Cisco person looking for in communications, as you would know, the type of traffic, the bandwidth, the quality of service requirements, security, your availability requirements. All of these things need to be considered. Availability may be seen as very important, but it comes at a price, it comes at a cost. Is it really important for every single endpoint? Where is it most appropriate? Is it driven by an internal requirement from the business? Is it driven by a regulatory requirement for uptime? Understanding these considerations helps us justify the investment in the comms technology that we're choosing to position at a given location. So we'll move on to the Western Power Distribution case study, which is what we were really here to talk about. And the methodology that we just talked about in the last few slides was there to help you understand the approach that Cisco took when working with Western Power for how we helped them derive their use cases and also derive their solution blueprint for how we undertook this trial. So just quickly, Western Power Distribution, for those of you who don't know, is a distribution utility in the United Kingdom. It's in the Midlands and Wales area. As you can see, they're a holding company that owns 4 distribution licenses across the United Kingdom. A customer base of roughly 8 million, as you can see there. Very long length of overhead lines and underground cables to 184,000 secondary substations, to give you some idea of scale. The Falcon project, as you can see, stands for Flexible Approaches for a Low Carbon Optimized Network. That was a term that was obviously used by the Western Power people and the government in the United Kingdom. To summarise what the project was about, the project was entirely about understanding whether or not a case exists for specific grid reinforcement or intervention techniques, and whether or not the investment in all these various smart grid applications or technologies would actually derive a benefit for the United Kingdom. I hope we got a triple arm for that, of some sort. Okay. Did everyone hear everything earlier though?
Can you start over?
Right. We'll start from the beginning. Flexible approaches for low carbon optimized networks. So as you can see, what we've highlighted here is the area where Western Power distribution operates. It's basically from the supply point right down to the meter. So I'll let you go through that, but basically what we're looking at is to understand the cost-benefit approach of introducing these intervention techniques within representative parts of their network, and whether or not there is a case for the United Kingdom regulator to approve Western Power and other utilities to roll these technologies out across the United Kingdom. That is, trial the solution first, understand the benefits before we invest in a full-scale rollout. The other key requirement for this particular project, as a government-funded project, they wanted to ensure that the learning outcomes were disseminated so that all distributors in the United Kingdom could gain from the understandings, because they all operate under the same benefit. That information is obviously available publicly and can obviously be subscribed to. So what Cisco's done is taken in some of the more common use cases across the different parts of the grid: the consumer, the distribution part of the grid, the transmission part of the grid, understanding where are we going to be focusing on, what is it that you're asking us to help you with. And once we understood the specific use cases that Western Power would be looking at, it then became clearer for us to start the conversation around requirements and how we're going to start to position the solution that is going to be there to enable these use cases. As you can see here, these were the particular use cases that were in scope for the study that we needed to undertake. And as you can see, with no transmission-based use cases, there was no need for us to focus on things like PMUs and phasor measurements, etc., because they just simply were not in scope. So the comms requirements, though, were very common, or typical, if I could use that word, for any given utility smart grid. It's to provide a secure and reliable infrastructure across, for the pilot, it was 9 primary substations and 200 secondary substations. Very representative sample area. The communications had to transport both monitoring, so that observation, and control-related traffic, so the ability to action commands to these secondary substations for the particular intervention techniques. Mandated by Western Power was that the internet protocol would be utilised for all communications requirements. We had a unique constraint with them in that there is no copper, fibre or any other wired service to any of these locations. Everything was delivered currently over UHF when we first arrived, and is now evolved to a new radio solution, which in the case of the United Kingdom was chosen to be WiMAX, basically. The substation technology for each of the primary and secondary substations was to be derived based on IEC 61850 as part of the trial, and a constraint that was applied was that no fibre or pilot or copper wires were to be installed anywhere. There is a complete restriction on that in the United Kingdom, which personally I found to be quite challenging when we first showed up, because virtually every utility has lots of wires to every substation they have, but this was the first time I came across a utility or a market where the wires don't exist. You actually needed to use radio technologies. They had already trialled and completely ruled out any form of GPRS-based technologies, so cellular variants. They basically did not want to use a public carrier as their primary bearer of traffic. They had completely ruled that out as an option. So the 4 intervention techniques that were to be looked at and experimented were dynamic asset rating, automatic load transfers, meshed networks, and energy storage. So you can see the objectives there for dynamic asset rating. We wanted to maximise the network capacity usage by monitoring their temperature and load, and then using that information to calculate real-time capacity. That was the entire objective of that first technique. Is that worth deploying that particular technique right across their service territory? Technique 2, change the configuration of the actual network. This is the electrical network, to improve the flow of power via the rerouting of load during different times of the day. As the peaks occur, reroute the power to a different part of the network. Mesh networks was effectively a closed network, but allowing the null point to automatically load itself to the appropriate point. So basically keeping the network closed, monitoring the temperature and load, and allowing the network to find its own natural balancing point. And then energy storage was the installation of batteries on the network, effectively distributed storage as a use case, and seeing whether or not we could reduce the problem of network peak loads and the cost modelling associated with that versus the benefit. So, dynamic asset rating, use case 1. So, the current asset rating, today, they build a 50% redundancy load into many of the networks, and the United Kingdom was no different. They were doing exactly the same approach. They basically had their entire secondary network as being unmonitored, so no visibility of what's going on in their secondary substations. Some of the assets were underutilised, which they knew. Some were overutilised, particularly in the winter time when all the heating kicked in and was turned on. The static ratings today were used for certain periods, and the renewable generation was forecast to increase what was occurring in their networks, in the secondary part of the network. So what they were looking at with dynamic asset rating was to move to a situation where they could monitor the voltage and current and the environmentals all at the same time and get that information back. They wanted to rate the asset based on those measurements, not based on what they already had in their design spec. Based on those ratings and what they had, they then wanted to be able to make a decision to drive heavier or lighter loads through those given feeders. And basically, through that process, they wanted to achieve the outcome of maximising their asset lifetime. So where are we looking at? Locations. We had the control centre being involved, the primary substations being involved, and the secondary substations, in particular the feeders and the transformer, being involved. The devices, or the technology electrical grid devices that were in play, obviously the SCADA system at the control centre, the RTUs out in the field, particularly at the transformers, the dynamic asset relays that were taking all the measurements, and the line power sensors, as you can see a picture up there, was on the feeder, which were deployed just to take in those measurements. Okay? From a communication point of view, what we needed to understand was what is the interaction of comms between those various devices. So we knew there was RTU polled values that needed to be brought back to the SCADA environment. We had some threshold alerting that needed to be created into their environment. We had some ampacity readings that needed to be monitored in real time and fed back to their SCADA environment. And we also needed to ensure that the control signals from the transformers were also being fed back into the SCADA environment so that intelligent decisions could be taken. So what we've done is, to understand those flows and understand the requirements from a communications perspective to what would need to take place, is we've looked at the individual message types that have occurred between the RTU, the sensors, the relay, and the DMS system. And if you break it down, you can see there that the RTU associated with the transformer is hardwired into the sensors, which is how it was set up in the field, hardwired into the relay. Relay and the RTU are basically both connected to the same sensors. They're then feeding back that information to the DMS system. And you can see that the RTU is reporting status, it's reporting fault events, and it's accepting control commands from the SCADA environment. Whereas the relay was simply recording the ampacity readings back to the SCADA system via a different path. For the non-operational flows, that is network control or network management or faults, etc., to do with the devices themselves, we've got some database uploads from the RTU, which is just blank files or files effectively that needed to be uploaded. Firmware downloads needed to be considered because they wanted to be able to manage this network over this particular infrastructure that was deployed. Device configuration information and time synchronization. This was the other requirement that needed to be accounted for. These are all non-operational flows, though, as far as the grid was concerned. These were the control information for how we manage these particular devices in the field. But nonetheless, they needed to be considered. Part of the challenge we had was, because this was new technology, Western Power's engineers did not want the existing UHF radio comms network to be disconnected from any of these devices while this particular trial was occurring. Effectively, there was a period where the confidence needed to be brought up that the technologies that were being deployed would actually be suitable before they start disconnecting any of the existing technology. So as you can see at the top half, I'll just go through this quickly, that blue line at the top is the existing UHF radio, UHF SCADA-based network, talking to an RTU in the field and continuing to talk out to all the individual devices. A clear rule or a mandate that was put on the entire project was that nothing is to interfere with that existing communication pathway. It must be all done separate to that. So what we needed to do was to build in parallel a separate communications network adjacent to it and interface our network into that existing infrastructure without touching the existing radio or UHF environment, which you can see is what we've done here. We've got effectively the new IP communications network, which was built over a WiMAX infrastructure through their primary substations and then out via WiMAX again to all the secondary substations. We'll get into a little bit more detail about the comms architecture itself, but just to give you an overview, at the control center and the head end, the ability to come via a different IP pathway was completely new to the operational engineers within Western Power. And it takes a little bit of time for them to obviously upskill and then have the confidence that the infrastructure that's being put in place is actually there to help them and give them more information. It's not there to take away from what they're doing today. Use case 2, automatic load transfer via an open ring. So the traditional topology of 2 or more routes from the primary station through a ring of secondary substations is what has been followed in the United Kingdom. There's an open ring with the open point being the null point, which is obviously determined based on the load throughout the time of day. For example, you may have heavy industry on a part of the feeder or commercial, for example, at a particular time of day, but when they power down in the evening and the residential load comes on, they may shift the load effectively. Each secondary substation is then connected via the one supply route through the day period, but obviously has reroute capability via a secondary path. What they were looking for was automatic load transfer capability, where we are able to dynamically alter the number of secondary substations that are on the circuit during the day based on the load conditions. That decision would not be based on time, it would not be based on operator intervention, instead it would be based on measurement, based on the data of what was occurring in the network to optimize it at the time. Basically, what they were hoping to do was to remove the need for the operator to be involved in this process, to remove the need for time-scheduled activities to take place, to put it back to the SCADA system to make an intelligent decision based on the measurements that were being taken. PMUs were put in place just to measure the impact on the grid. They weren't used for anything other than research purposes, just to take measurements effectively, again, to understand the changes in the network and what occurred so that that data could be collated and then disseminated after the fact. So they did use PMUs for that purpose, but it wasn't part of the intervention technique. For the actual solution, sectionalizers were used throughout the network, and as you can see, particularly between those 2 substations there on the left-hand side, a ring is created out to all the individual secondary substations. And what happened is, as you can see at the end, there is an open circuit at the end, which allows the load to be balanced on both halves of the ring. But based on the measurements of the load at each of those transformers throughout the day, when the load shifts from a particular area, such as commercial property, etc., powering down towards the evening and residential load increasing, that data back at the management system would then be intelligently acted on, such that the DMS system is able to communicate with those sectionalizers to reconfigure them to rebalance the load over that network and effectively allow the power to be rerouted automatically. In understanding the the way the network behaved and the benefits that they were getting via all the measurements, what, again, Western Power was seeking to do here was to understand what benefit are they going to get by introducing this type of technology into multiple secondary low voltage network sections of the grid. And is there a business case to invest in this technology for a wider scale rollout across the 180-odd thousand secondary substations that they have? Again, the locations that were in scope for this particular intervention technique: the control center, the primary, the secondary substation, and the pole top itself with the sectionalizers. The devices that were in play: the DMS, or the control center from the SCADA point of view, the RTUs, the sectionalizers, and the phasor measurement units, which are obviously there to gather the data. From a communications perspective, we needed to poll the RTUs, as was always the case. We needed threshold alerts. We were taking a PMU data stream back, and we were using control signals for the sectionalizers, initiated from the SCADA system out to the sectionalizer. Again, we've looked at the operational flows that occur between these particular endpoints. We've looked at a measurement, we've looked at a report fault event, we've looked at breaker control events, and we've looked at the phasor measurement events. If you look specifically within each event, we had a basic category. We're looking at bandwidth, we're looking at latency, we're looking at the resiliency requirement, the security requirement, and whether or not there is a jitter requirement. By understanding those metrics and those parameters for all the given operational flows, we can understand the requirement that is going to be there for that part of the network. If there is a high bandwidth requirement, as you can see, all of these are low bandwidth, but if there is a high bandwidth requirement, clearly a low bandwidth radio technology may not be fit for purpose for application in that part of the network. There's no point deploying a non-fit for purpose technology if it's not going to meet the requirement. So very similar to the last one, you can see here, over the radio technology, we were unable to get all the communications going. There was a public network for the RTU in this particular use case where the existing monitoring and control information was to remain. Again, as one of the conditions, we were not allowed to touch any of the existing communication flows that they had in place. Again, this was just a maturity thing and a confidence thing for Western Power. Once they had the confidence on the IP comms network pathway, those legacy, if I call it that way, networks, the UHF and GSM networks, were able to be disconnected. But at the time of the project, they were maintained and in place for, I guess, duplication of data effectively for non-pilot purposes. They were the actual operational loads. When they began the pilot, though, and actually started it, all traffic flipped from the DMS via the legacy pathway via the new pathway and the IP network interfaces. The mesh networks use case, it's very similar to the automatic load transfer. The main difference is, instead of having an open point in the network, which we had in the last use case, now we close the ring off and we allow the ring to find its natural null point. Where is the natural point of balance on its own that it can find to balance itself? And is there a benefit in just leaving the ring closed as opposed to talking to all the sectionalizers and having them open up and be controlled by the DMS system? That is the predominant difference between these two techniques. So rather than shifting the load operationally between routes using that switch gear, which is obviously requiring a lot of switches to be installed, the mesh network was a passive solution so that a permanent closed ring was created, giving you that virtual floating null point within the low voltage network. Multiple protection zones were then needed to be created to facilitate this particular network. And in this particular environment, they were actually operating protection over WiMAX. Now, for any of you here who are a protection background, you will know that protection requires a very low latency performing network. WiMAX is not a low latency technology, certainly not in that 0 to 10 millisecond range. So what they have done is they've engineered far more conservative protection schemes where they're more tolerant of longer latencies in order to allow for the delay or the latency within a WiMAX infrastructure. Can we engineer sufficient protection and a sufficient buffer, even allowing for the latency of a WiMAX-based infrastructure? That was part of the discovery and the testing as to whether or not we can extend protection down to the low voltage network environment or not. Remember, as I said earlier, there is no copper pilot or fibre pilots to any of these locations today. Everything is done over UHF. Can we move that towards a WiMAX environment? The power flow is improved as the mesh allows the current to choose the path of least resistance. So basically, based on the load in the network, it automatically just decides where the load is going to be balanced across that particular network as a closed ring. So as you can see there, it's very similar to the last diagram, except over here on the right, we actually have a closed circuit. We're no longer open with a breaker or a sectionalizer. And effectively, we're running 3 protection schemes now. We're running directional overcurrent with a blocking scheme at 200 millisecond requirement of latency there. We're also running overcurrent protection and current differential. And that was what needed to be tested as to whether or not this particular intervention technique would be valid to be deployed on a wider scale. The locations, again, very similar. Control center, primary substation, secondary substation were involved. The SCADA environment was needed, the RTU, the individual breakers at each of those secondary locations, and the protection relays that were deployed. The communications that were required, RTU pole values of threshold alerts and 11 kV teleprotection services were deployed and tested. So how does that network look in the field? As you can see here, what they're looking to do is, this is actually a typical secondary substation in the United Kingdom over here on the left-hand side. It's just a hut, effectively. If you open it up inside, you can see what's inside. Very common for what you would see inside a secondary at any given location. Again, what we've looked at is the actual operational flows, and you can see the big new one here is the protection message, and in particular the 61850 goose messaging in this particular operational flow decomposition. You can see here what we're doing is a protection relay which is hardwired to a breaker now needs direct communication to the next protection relay via goose messaging. That particular flow there is over a WiMAX infrastructure, so it had to tolerate the 200 millisecond latency requirement. Effectively, that is a constraint on the protection scheme as a whole that the protection engineers need to account for in terms of they have a delay on their breaker closing, which is what, 100 milliseconds. They have a delay in the message itself, 200 milliseconds. And if they could not engineer a protection scheme that was capable of tolerating those delays, then that protection scheme may or may not be proven to be invalid for usage. You can see here how the requirements for teleprotection are completely different to those of the operational flows, for example, of measurement. Again, the architecture, as you can see here, what we've done is we've taken into account the fact that there were multiple secondary substations that need to talk to each other via a primary substation as well, but the protection relays need to be able to directly communicate with each other now via this WiMAX backhaul. The fourth use case was about battery storage, and in particular, installing them at the ground-mounted secondary substations was where they were looking at deploying it. Basically, charge the batteries up during low demand time, discharge the batteries during high demand to provide extra voltage support to that part of the network during times of high demand. Batteries were always installed on the low voltage side of the transformer, and they were always hosted at the transformer. The charging and discharging regime, it was controlled by algorithms responding to network demand. So basically pre-programmed into the system. Distributed control, centralized control was available to those battery controllers, but predominantly it was being run out of the distributed control model where the controller for the battery itself was making the decision to begin either charging or discharging accordingly based on the measurements in the network. So again, you can see here what the battery shed looked like. It was quite large, effectively adjacent to the substation itself, and this proved to be a level of problem, particularly with community concerns where they didn't want to see another shed or another large structure being installed in effectively what were community suburbs, etc. So it was proving to be a problem. But the locations that are involved, the control centre and the secondary substation, we're looking at the SCADA system talking to an RTU, which is then talking to the energy storage unit. The communication requirements, it's just pole values to the RTU, threshold alerting, and then the monitor and control system messages. Again, if you decompose all of the operational flows from the various systems, you can see how they worked. We had information from the storage unit itself now talking back to the battery management system, which was hosted at the control centre, separate from the SCADA environment. The SCADA environment continued to talk to the RTUs at the given location, but the RTU would make decisions as to whether or not it was going to allow or accept power from the energy storage unit via goose message interfacing. So you can see how the system has been put together, and each application flow is being decomposed and understood so that we can then understand what the underlying foundation of the comms fabric needs to look like. It was a very simple use case, this particular one. Straight out to the secondary substation, interface the battery storage unit directly through the local router to the RTU at the given location to facilitate the goose messaging over Ethernet. So a solution overview. What did the comms solution look like at the end of that to facilitate those intervention techniques? So at a physical layer, if you take the grid as a whole, when you come down to the low voltage network, the control center was already established. As you know, the SCADA environment was already in place. Out to 2 microwave towers, which is where the WiMAX network effectively began. But basically, using the microwave backhaul from the control center to 2 radio site locations, we're able to provide high bandwidth backhaul comms. But then from those towers, the WiMAX network began. And the WiMAX network was radiated out to 9 primary substations, which effectively acted as the WiMAX base stations. And then from those 9 primary substations, we interconnected 200, as you can see at the bottom, 200 equivalent secondary substations per the transformers on top of the overhead power lines. All of those were interconnected via the WiMAX sector design. If those of you are asking who was the WiMAX provider, no, it was not Cisco, it was Airspan. Cisco does not provide WiMAX-based radio solutions, so we had collaborated with Airspan as the WiMAX solution provider. What Airspan were responsible for was providing the WiMAX radio cells and for providing the WiMAX radio plan. What Cisco was responsible for is ensuring that the WiMAX infrastructure ran an IP infrastructure and the quality of service and security necessary to run the end-to-end solution. So if you can think of Cisco as running the overlay and the entire solution architecture, the subcomponent of WiMAX radio was taken on board by Airspan.
Were you managing that through an existing network management system? You have to bring your own?
The Airspan radio network, it wasn't managed in this particular trial because it was only the 9 base station sites. There was no network management system deployed.
What were the references? I can't see those 2 NMS in the control center.
Cisco, so the connected grid network management system was deployed to manage all the CGR routers. The Airspan system was brought in, but they didn't proceed with it in the end. I don't know if it ended up going through in the end, but based on typical project concerns at the time, they didn't proceed at the time. But that's how it looked from a physical topology point of view. From a logical point of view, as in from an layer 3 IP network point of view, it ended up looking like multiple secondary substations on the same common broadcast domain, or VLAN if you prefer, across the WiMAX infrastructure. So you had sectors being created upon which individual substations could then be joined onto the same IP segment. Effectively, that allowed then all those various RTUs, IEDs, and various other devices to be interconnected over the one IP-based network infrastructure. you can see there how everything was then interconnected together as a representative model. From the WiMAX point of view, you can see the black triangle in the middle, for example, is one of those microwave towers that were deployed originally. The red dots are the primary substations where the WiMAX radio base stations would begin. And then all those individual yellow dots are your secondary substation locations where we needed to provide sufficient coverage to be able to reach via connectivity. As you can see, the RF band was being used with 1.4 gigahertz. Western Power didn't actually own the spectrum. It's owned by the Ministry of Defence in the United Kingdom. But for the purposes of the trial, that spectrum was made available to Western Power Distribution with the view that the Ministry of Defence may relinquish that entire spectrum to the utility sector in the United Kingdom if appropriate to do so. The substation connectivity, if you can have a look at the top diagram there, that's the primary substation. We had a very simple architecture. It's a Cisco CGR 2010 router, which is our connected grid substation routers. We basically had a number of devices in the design. We had a very replicable model for 9 sites, every device connected to the same port at the given location. There was no need to change the way things were physically connected. And at the secondary substations, it was the connected grid field area router, the 1240 series for outdoor pole top mounting. And very similarly, devices were connected to that router via the same physical interfaces at every location wherever it was possible to do so. The same devices typically existed at every given location. It makes complete sense to keep it all consistent. Just to give you an indication of some of the locations of where it was deployed, you can see up there in the top in one of the secondary locations, the CGR was actually deployed inside the building. You can see here on the bottom right, it's actually deployed behind a substation building with the antenna array going out to the top, which is via those flat panels. What they found was a problem with vandalism started to occur where those antennas were effectively being knocked off by teenagers and the like, so ended up having to change those out into starting to use some low profile antennas, which would reduce the vandalism incidents. But that was something they had actually not counted on and did not expect to have take place. As I mentioned earlier, this whole project was all about learning and dissemination of information. There was no right or wrong answer for any of these proposed techniques. What they wanted to know was, if we test this technique, what is the result we can see in the United Kingdom market scenario, and based on that information and being shared, we can then make decisions as to how we proceed further to next steps. So those learnings have been published via a series of white papers, external-based case studies, some video on demand, VODs have been created, and there's some joint industry presentations that have been created as well. I've got a few minutes here. We'll just ask the people at the back to click a link, which will just let you listen to some of the people from Western Power about this project.
The world's energy consumption is accelerating exponentially. However, it is imperative for our future that we reduce carbon emissions. By 2050, the UK wants to reduce carbon dioxide emissions by 80%. Western Power Distribution is working to make this a reality. We need to manage new energy demands in peaks and troughs of consumption to make sure the lights stay on for our customers. We need a smarter, more flexible grid. We need to design and manage the networks in ways we have never explored before.
Reliable and secure near real-time communications is a key element to the Falcon project and to all smart grid deployments.
The telecommunications and the data management within our low carbon network fund projects such as Falcon is the smart in smart grid.
So the benefits of Project Falcon are to increase the capacity of the network within the Milton Keynes area and to enable customers to connect low carbon technologies.
Cisco is responsible for the design and supply of a secured communications infrastructure required to remotely monitor and control the substations involved in Falcon grid reinforcement techniques.
The Falcon project will use a converged IP and Ethernet communications infrastructure. This securely allows monitoring, control and protection of the techniques being trialled.
We started the journey with a deep understanding of Falcon's functional requirements, smart grid use cases, and derived the communication requirements. We then identified the electrical grid and physical communication infrastructure existing on the trial field. Then our architects designed the end-to-end secured communication infrastructure, fulfilling the requirements of the intervention techniques.
Cisco's role within Project Falcon has been absolutely critical. They've not only brought in their expertise around telecommunications and networks, but they've also been able to share with us how they're working with utilities and distribution network businesses elsewhere across the world.
The network connects the Western Power Distribution Control Centres to the primary substations and the secondary substations using a private WiMAX radio solution. A hardened set of network devices within each of the substations will provide Ethernet connectivity and access to the wide area network. Internet protocol will be used to transmit all data to and from the substations.
Cisco provided utility-hardened smart grid communication equipment for the trial implementation and testing.
Cisco have exceeded expectations within Project Falcon. They've been flexible, they've been diplomatic, and their expertise has been second to none.
What we've learned from the Falcon project will be the glue that binds all of our learning together. Because without the telecommunications and without the data management, we won't have the smart grid.
Okay, so just to conclude, the lessons learned, basically from a technology perspective, let alone the electrical perspective, radio planning in particular for the United Kingdom was critical for spectrum to be allocated. Without the spectrum allocation, there was no technology, there was no solution. So they have a in-country government argument that they need to take up as a in-country organisation to get that allocated. There was no substitute otherwise available that we could utilise. The physical network, understanding the connectivity requirements, understanding that the physical network can now be decoupled or abstracted from the application layer logic. It doesn't need to be tied hand in hand. This is how you enable the multi-service environment. Integration with the control centre, the existing control centre, was clearly a critical requirement because all of this grid control system still needs to be monitored and controlled from the same control room environments. The IP addressing scheme is clearly overlooked. In fact, one of the requirements that they originally wanted to deploy was the same IP address at every single location so that when they configure a particular relay or unit, it can be factory configured with the same IP address every single place, and clearly it would just roll out with no complication. However, when you do that, that then becomes a problem in the field where how do you make a network operate when you have overlapping address space? So there was a clear misunderstanding on their part of how IP networks work and how NAT can be used to resolve overlapping IP address spaces. The security consideration, understanding that network ports or wireless network ports that are out in the field now present as a point of ingress to your cybersecurity environment, and in particular, it presents an external point of ingress at ground height to your control center environment. Understanding that port security, something as simple as securing that infrastructure both from a physical perspective and a cyber control perspective, was so critical for them to understand before they exposed their control room SCADA system to the outside world, which had previously not occurred. Understanding the role of these new protocols and new standards that were being employed from their proprietary UHF radio solutions and how using these new protocols was going to facilitate the intercommunication between all the devices. Everything from IP communications, but also IEC 61850 using DNP3 communications to the endpoints all over the IP fabric and then over the 802.16e WiMAX infrastructure. So with that, I'd open the floor to any questions that you may have.
I have some question. You have existing SCADA network. Why you have to build a new network?
Yep.
And now you are operating POS system.
Sure. The current communications network that were being used were based on UHF radio and was only extended out as far as the primary substation locations. To scale UHF radio as an existing comms technology to potentially 180,000 substations, it's not going to scale. The technology will not work. The capacity of that network is inadequate. The number of units that would be required would be inadequate. It just simply is not fit for purpose when you look at the use case of what's going to be required and the number of locations. And so an alternative technology was required. As I mentioned at the beginning, there were some constraints put on us as a solution provider. We could not use any fixed wire technology, so that ruled out fibre, copper, DSL, etc. You couldn't use things like microwave. It's completely inappropriate for that kind of technology requirement. They did not want us to use any cellular infrastructure. They did not want to have any reliance on a public cellular provider. So they had no spectrum. No spectrum was available until it was authorised as a loan from the Ministry of Defence. So our hands were quite tied. They came back and said, we are now mandating the use of WiMAX. WiMAX is what we are using. That's what we've been granted spectrum for, and we are looking at a WiMAX rollout. Whether or not WiMAX is the right choice of technology, it is what is available for the UK at that point in time. So that is what we had to integrate with. That gave them, in what they believed at the time, the technology that worked on the available spectrum, and it gave them the capacity for the use cases that were in scope for the Falcon project. And so that's what we had to work with. If I go back to the original UHF technology, UHF could have been used for the purposes of the trial because it was only to 200 sites, and that could have happened, but it clearly has no capability of scaling beyond that. The UHF would not be able to support layer 2 goose messages over Ethernet. It would not support DNP3 over IP or any of the new protocols that they were looking to enable, which UHF would simply not be able to provide. It was only providing legacy serial communication. Does that answer the question?
If I want to build IP-based network on fiber cable, can you compare between solution with fiber cable and WiMAX?
As to how it would behave or how it would operate? So sure, if you use fiber, you're eliminating all of the WiMAX backhaul, and you're clearly eliminating the dependency on spectrum. You're increasing your capability of achieving higher bandwidth application, but almost certainly you would need to have a different aggregation, such as a wide area network, to be created behind the field area network. You're not going to deploy fiber to 180,000 endpoints specifically from a hub and spoke model. You're going to have some sort of wide area network core, which then would extend out into the field area network to all the given locations. How you tier that network so that it can scale in a replicable manner across a country or a continent is what you would need to look at. For some of our customers who do have the luxury, if you like, of fibre assets, we do help them with that. We do help at identifying where it's appropriate to use fibre and where it's not. Typically what we find is that between the primary substations, that's where all the fibre does exist and is readily available. In the primary substations is where you can have communications infrastructure deployed in a secured facility because it is a substation. Out to the secondary substations, when you're out to little huts, green boxes on top of power poles, that becomes less appropriate to use fibre to those particular locations. That's where a choice of backhaul technologies becomes an option. Sometimes it's satellite, sometimes it's cellular, sometimes it's fibre, sometimes it's microwave. It depends on the given utility's requirements in their particular service territory.
Last question. Is there any problem when you transfer teleprotection signal over IP network?
I'll apologise. Can you repeat the question again? Just one more time.
Is there any problem when you transfer teleprotection signal over IP network? Because round trip delay of IP network more than TDM network.
Yeah, so the first problem is we don't transport the teleprotection over IP. We were doing it over Ethernet segments only, so layer 2. There was no teleprotection over layer 3. Yes, there are challenges with doing teleprotection over the WAN. Traditionally, you do have a low latency network requirement there. In this particular instance, we understood the latency challenge that was involved, and we put it back to the protection engineers that their scheme needs to be able to tolerate this additional latency, and if their scheme can't tolerate it, then the comms technology is not available for them to deploy teleprotection in this particular part of the grid. If there is a use case which required stricter latency requirements than what that particular comms network could provide, we would just simply said we cannot meet the requirement. It's as simple as that. Just because the requirement is there does not always mean that we can deliver to that requirement. And when we can't deliver to it, we call it out and say we cannot meet that challenge. Then it's back to the customer, in particular the protection engineer, as to what they want to do to remediate the problem. It's not something we can solve at that point.
Thank you.
Hi, Ronnie. It was a great presentation. I had the opportunity to actually visit Western Power Distribution last year. And I just wanted to follow up if the pilot has completed, the studies has completed, and if any utilities actually adopted any of those use cases, and were there any business case actually for those, any of those business cases?
Good question. So the pilot has finished up. The information has been disseminated, so back through the UK regulators, as to whether anyone has adopted and begun rolling it out. It would not be in rollout phase, it would only be in their planning cycles for obviously ongoing regulatory submissions and the like. I can certainly find out and come back to you with information on that if you like, and get a latest update. I'll reach out to Andy, as you met, and find out where we're up to in that particular question. Remind me to write to him today. I'll see if we can get one for you tomorrow.
And Ronnie, you showed us the lessons learned of the, let's say, telecoms network implementation. Were there any lessons learned from the business outcomes? I mean, the 4 cases, did you get any feedback from the customer of how it helped them, or?
Yep. So okay. Lots of lessons were learned from the customer as to the availability of that information. That information was disseminated back to the UK regulator, Ofgem, and it's their information to release to the other UK utilities. For the specific details of what has been done on the electrical network side and the business side, I can certainly follow up with the team in the UK to find out where that is and whether we have access to it, and also the level of, I guess, freedom we have to disseminate that information further.
I think that would be awesome. No more questions? Thank you very much, Ronnie.
No problem. Thank you for your time, everyone.
So before we take a break, we tried to show you that IoT is not just one thing. It's also not an end product that you buy. IoT, IoE, when you add the collaboration and the processes, it's a journey. And it's for each of you to decide where your journey starts. When you look at the presentation from Ronnie and you saw all the different use cases, in transmission, in distribution, in metering, in what we heard from Hydro about theft, about auto load balancing, all those. It is the takeaway probably for you to look at where is my opportunity, what are the particular challenges that I'm looking at, and where can I give it a try? Where can I start, have a case that is scoped, and where I can create an outcome that can give me some information that I can take to the leadership, to the board, but also that you can turn into a plan of what your end stage of IoT, IoE should look like. So it's probably one of the takeaways that I had. It doesn't matter where you start, as long as you start somewhere where it makes sense for your company and where you can get some results to help you steer in the right direction or take the next decisions. Would you agree with that, Dave?
Absolutely. I mean, I think as each of us talked to today, there's specific use cases depending on one jurisdiction, whether you've got regulatory constraints or a business case to drive something such as load loss or sectionalizers or replacement of a very legacy network such as what we just heard. There's value, but it all depends on the appetite of your executive, the appetite of your regulator, the appetite of your board of directors.
Yeah. So whether
It's up to us to convince them.
Exactly. So, and whether you start in transmission, in distribution, in metering, whether your case is how do I manage the grid, or how do I reduce theft, or how do I go into a predictive maintenance, that's probably your challenge, because my encouragement would be with the automation, you can probably address any use case. And probably with the automation that you choose, you can actually support multiple use cases. You have to find that place to start. And of course, I mean, by talking with your colleagues who already have done it, talking with our partners like Itron, where can I start? Talking with Ronnie and his colleagues, can you help me do sort of a discovery where to start? We're very happy to do that. Don't let it be so overwhelming that you don't start, because the opportunities are just too big to let them lie on the table. Not just for Cisco selling stuff to you, no, for you in running your business.